In this video, we're going to prove that the closure of S contains S, and that the closure of S is equal to S if and only if S is closed. So let's first talk about what the closure of a set S is. So if a set S is in a metric space E, then the closure of S, that we denote S bar, this S with the bar on top, with this line on top, is defined to be the intersection of all closed subsets of E that contain S. So I'm going to kind of show you what this looks like, both analytically and in maybe a pictorial form. But I encourage you to think more about the analytical definition than the pictorial form, because I've noticed in my attempts to prove different problems and real analysis and other areas of math that sometimes when I only rely on my geometric notion of something, it sometimes limits my problem-solving capability. So let's talk about the analytic maybe let's draw this out analytically first. So it's the closure of S is the intersection of all closed subsets of E that contain S. So let's think about all the closed subsets of E that contain S. Let's think about maybe the collection of all closed subsets of E that contain S. So this is maybe a collection of closed subsets, and so such that G alpha contains S and G alpha is closed. So we can think of this collection right here, this collection of closed subsets of E, as the collection of all closed subsets of E that contain S. So if I want to write the intersection of all closed subsets of E that contain S, and right here, look at this, I have this collection of closed subsets of E that contain S. This is, in this collection, in this set of sets right here, this is a set of sets. In this collection are all possible closed subsets of E that contain S. So therefore, the closure of S is going to be equal to the intersection of all of these sets, or to say intersection of all these alpha. And a lot of times I've talked about in previous videos, you can say alpha and I, where I is the indexing set. This indexing set is a list or a set of indices, so that we can distinguish each of these G alphas. But that's if we can also, some people also write it with just the alpha on the bottom. So S closure is equal to the intersection of all of these G alpha. And so that's helpful to note, that if I have a collection of all of the sets of all of the closed sets in the metric space E, if I have that collection of all the closed sets of the metric space E that contain S, then the intersection of all of those closed subsets is equal to the closure of S. And maybe a way to draw this would be if I have my set S here, and I have my metric space E, then maybe one possibility of what this might look like if we were to think about it geometrically would be all of my closed subsets, I'll write them in red. So maybe something like that, and something like that. And maybe I'll have a closed subset that's really close to E. Really close to S. This blue set is S. I should have said that beforehand. This is S, and then this is E, this outside set. And all of these red and green sets are closed subsets that contain S. So the intersection of all of these sets would be what is in green here. The intersection of all of these sets would be the set in green here. The intersection of all the sets, all the closed subsets that contain S is everything in green here. Okay, so now that we have an intuition behind what the closure of S is, let's prove first that the closure of S contains S. So let's prove number 1 here. So if I want to prove that the closure of S contains S, that is to say that S is a subset of the closure of S, Remember that by definition of subset, of how we define subset, or what it means for a set to be the subset of another set, I have to show that if I take any element in here, then it must also be in here. So let's take an element in S. Let X be in S. Then I want to show that, or in fact, we will show that X is in the closure of S. So this is what we want. This is what our goal is. This is what our goal is. We will show that X is in the closure of S. Well, if X is in S, remember, and oh, by the way, let me emphasize here that something we might be shooting for is I want to show if X is in S. So if I want to show that X is in the closure of S, then if I can show that it's in the intersection of all of the closed subsets of E, the metric space E, remember S is in the metric space E. If I can show that X is in the intersection of all of the closed subsets of E that contain S, then I'll have shown that X is also in S, the closure of S, and I'll be done. So if I want to show that it's in the closure, if I want to show this in the closure of S, then that means I want to show that it's in the intersection of all of the closed subsets that contain S. But if I want to show that it's in the intersection of all the closed subsets that contain S, remember, if X is in A intersect B, this is just an aside here. This is just an aside. If X is in A intersect B, then that implies that X is in A and X is in B. Not only that does that imply, this is equivalent to. So if I say that X is in A and X is in B, then that means that X is in the intersection of A and B. So if I had the intersection of an arbitrary, if I have an intersection of an arbitrary number of sets, if I have an intersection of an arbitrary number of sets, that is to say, a family of intersections of sets. So A intersect B, intersect C, intersect, and so on. It doesn't have to be a finite number. It could be and it doesn't have to be a countably infinite number. It could be an uncountably infinite number of sets. Then I have to show that if I want to show that X is in this intersection, then I have to show that X is in each of these sets A, B, C, and so on. So if I want to show that X is in this intersection here, then I have to show that X is in G alpha for every G alpha in this set. So, check this out. I can do that in the following way. If I know that X is in S, if X is in S, then take any G alpha in my collection of closed subsets that contain S in G alpha. Well, then we know that since G alpha is a closed subset that contains S, then this implies another way to say that G alpha contains S. So remember, G alpha contains S. That is to say that S is a subset of G alpha. So everything in S is also in G alpha for every G alpha in this collection of closed subsets that contain S. So since X is in S, that implies that X is in G alpha for every G alpha in this collection of closed subsets that contain S. So therefore, X, since X is in every G alpha for all the G alpha in this collection of closed subsets that contain S, then that means that X is in the intersection. Remember, I just shown by that statement, by this statement alone, if X is in G alpha for all G alpha in the collection of closed subsets G alpha that contain S, then I've shown that's in each set in the intersection. So therefore, it is in the intersection of all of these G alpha, which is the same as saying that X is in the closure of S. And we've just proven part 1 here.